Hello everyone, my name is Ivan, and our today topic is in-memory computing meets database durability, best practices for native persistence and data recovery. What I'm going to tell you about is how to combine in-memory computing when you store all your data in RAM in order to gain maximum performance with durability. I will tell you how the durability mode can handle some of your use cases. And also, I work as a senior engineer in grid-gain systems. I work with Apache Ignite. And I have hands-on experience with developing durability modes. I'll shed a light how it's implemented, how to easily attach durability to your in-memory system. And then I'll tell how to cook your durability mode properly to achieve maximum performance and solve your use cases. My talk will be divided into 4 parts. First of all, we'll speak about what features do in-memory data grids lack. They are good, they provide good performance, but there are some disadvantages that may disappoint you. Then we'll take a bit deep dive into architecture. We'll consider how durability mode is implemented in Apache Ignite and with a transparent page memory architecture. Then we'll move from theory to practice. We'll discuss several use cases. We'll start with storage management. I'll tell you how to configure your cluster in order to work with persistence and limit your memory and disk usage. And then we'll proceed to data backup use cases. I'll tell you what data backups are and how to use them in different options. And at last, we'll move to the section about performance tricks. One way or another, if you use persistence, you may experience some drop down of your performance because you write to disk anyway and it may be slow. And I'll tell you how to handle and what to know about in order to minimize the overhead of using persistence. Okay, let's start. Let's talk about in-memory data grids. Commonly speaking, data grids are caches, distributed caches with brain. They allows you to store your data in a distributed environment and not only store and access your data and also perform some complex stuff about your data. First of all, it's distributed computing, when you can specify MapReduce like task in order to computate something in your cluster and assemble and aggregate results of your computation. And you can use data grid as cache to third-party storage. You can use a separate database and work with data grid in write-through or read-through mode. And this is awesome, but you may experience some disadvantages. First of all, if you decide to store your data in memory, perhaps you don't want to store all of your data in memory mode, because your data may be separated. You may have operational data set when in-memory speed is really needed. And on the other hand, you may have a historical data set, also referred as cold data. And perhaps you don't need the best in-memory speed for working with cold data, because storing all data in RAM is quite expensive. Storing data in RAM in production environment is expensive by a factor of 40 times. It's production level SSD costs 20 cents per gigabyte and RAM costs $8. And if you may optimize it, you may want to store only part of your data in RAM. Next point is that sooner or later your production distributed system may require a maintenance. You may want, for example, to upgrade version of your product. You may want to upgrade hardware But anyway, sooner or later you will need to restart your cluster. And if you restart your cluster with memory stored in RAM, you will lose your data for a moment after the moment of restart, and you will need to reload your data again manually. So it would be very handy if your cluster wouldn't require reloading data again and would just keep it, and you will have your data available. Next point is that anything that can go wrong will go wrong, and in case something bad will happen, you may corrupt your data scheme, you may update your data in erroneous way, you may want to perform Ctrl+Z, you may want to recover your previous state. And in the world of regular relational databases, this problem is already solved with data backups and data backups restoring. So it would be really handy if, when you work with in-memory system, if you had an opportunity to create and restore backups. And durability mode, which is a good addition to regular in-memory deployment, is a good addition that can solve all of these use cases. Okay, let's move to the lower level and talk about how we implemented durability mode. It's in Apache Ignite, it's implemented through transparent page memory architecture. What does it mean? Data is always stored in pages. All your memory that is used by your local node is split into small chunks, pages, and they also keep they always keep all the data. And there's abstraction that page in durability mode is always present on the disk, and only optionally it's present in RAM. And when you update your data, data accumulates new state of your structures and gets dirty. Dirty page is page that has new updates and is not yet synchronized with disk. And such dirty pages are accumulated in RAM. Sooner or later, you have to synchronize your state of your dirty pages with disk, and that's the moment when the checkpoint comes. Checkpoint is process of batch updating, batch synchronizing of all your page state to disk. It's the process that occurs from time to time, and it just dumps all changes to your persistent storage. The question is how to recover all your state after restart. Most likely, your latest changes were checkpointed and they are already on disk, but perhaps they are not. In case they are not, there's another option, and every update is also written to persistent journal that is called write-ahead log. It's kind of common abstraction for relational databases. And when your system crashes or gets shut down and you want to set it up and recover your latest state, all updates either get read from your disk storage, updates were checkpointed to disk storage, and if they were not, they will be read from write-ahead log. Ignite node will scan write-ahead log exactly from the moment of last successful checkpoint and recover your very latest updates. So one way or another, with these abstractions, all your data will be present. Quite a simple architecture, and let's proceed, and I'll now explain how do we create consistent data snapshots with this architecture under load. As I said, every page is always present on disk, so what we have to do is just to scan disk storage and copy all pages to a separate snapshot storage. It's quite simple, but there can be conflicts. There may be conflicting updates that are performed by concurrent checkpoints. Checkpoints update state of pages on disk, and when we create snapshot, we want to create a consistent state that represents state of the system for a certain point of time. And if pages that were not written yet by the checkpoint by the snapshot will be modified by checkpoint, we will bump into a problem. That's our state will not represent state of the system for the point of time. And what we do is cooperative cooperative working of snapshot and checkpoint processes. If checkpoint process comes and understands that it wants to update page that wasn't snapshotted yet, it helps snapshot process, and first of all, it writes old state of the page to the snapshot storage. After that, state of the page is overwritten by the new state, which is actual from perspective of a new operation. And at last, one way or another, all pages will be transferred to the snapshot storage, probably from regular snapshot disk scanning of all pages, or probably with cooperative write by checkpoint process. That is very good, but let me now explain how durability mode can be helpful for you. We'll talk about use cases, and I'll describe several use cases that may be helpful for you in your production. And then I'll tell you how to achieve the behavior that you want, configuring Ignite and configuring Ignite persistent mode. Let's start with storage management, and then we'll proceed to using data backups. What you may want, first of all, is to limit RAM usage of your Ignite node. You may want to do this for several reasons. First of all, you may want to not allocate all of your physical memory, because if operational system will run out of resources, it will behave poorly. And the other reason is that you may want to combine Apache Ignite with another distributed system. For example, we have experiences of deployments where Apache Ignite is used along with Kafka, each of them for several reasons. And you may want to divide your physical memory between Ignite and Kafka. Then we'll proceed to more specific configuration. For example, if you have several tables, several caches, you may want to divide memory between them proportionally. And I'll tell you how to achieve that. And then we'll finally move to benefits of using persistent mode. I'll tell you how to achieve a fast cluster restart and possible cheaper data storing, because storing on disk is cheaper. And the most typical use case when you want to divide and use cheaper data storing is when your data can be separated into hot and cold. And I'll tell you how to configure Ignite to achieve the best speed, like in-memory speed for hot data, and still achieve durability for cold data. First of all, let's start with the classical in-memory mode, and I'll tell you how to limit your memory usage. We can configure overall RAM limit, and this amount of memory will be allocated by your data, by your caches that you use on demand. There's a bin that's called data storage configuration in Apache Ignite, and what you may do is configure maximum size for your default data region. When you say that you want it to be 60 gigabytes, let's see what will happen. You will have 60 gigabyte chunk that will be allocated by Ignite node in RAM. And when you will load your data into your Ignite node, dependent on how much data in each cache you load, caches will allocate smaller chunks, smaller pages from this big chunk, and they will use it. So now you don't have control of how the memory will be distributed between caches, but you have control that overall memory usage won't exceed 60 gigabytes. Let's proceed to more specific configuration and to a case where you want to distribute your memory between your caches in proportional manner. You may configure several data regions, and you may set different limits for each region. And there's an option that you may configure an eviction mode. Default behavior for Ignite, when you exceed maximum size of your memory, your node will crash with a message like out of memory. You can change such behavior, and you can specify an eviction mode, and in such case a node won't crash, and all data above the limit will be just removed. Let's see how to configure it. You may configure two regions. First of all, first of them is not with eviction, it's bigger, and another one is smaller, but it has eviction configured. It's switched on by option set page eviction mode, and then the algorithm that you want to choose comes next. And in such case, there will be two chunks, and if you have already specified that cache A will work with smaller region and cache B with bigger, they will allocate and use memory in their own regions. Their memory usage will not intersect. And in case you will load more and more data to evictable region where cache A operates, when you exceed its memory limit, your node won't crash, and just all data will be evicted, and it will be removed completely. Ignite will traverse your pages and choose the oldest pages that are not actual, and data that is stored on such pages will be just removed. It's a good pattern to use that eviction mode when you work with Ignite exactly as with cache. For example, if you have a separate relational database that is main source of the data, and you use Ignite in order to speed up your activities, it's a good pattern, because if you have lost your data and it was evicted, it's not a problem. You will just reboot and reload your data from the third-party storage. It won't be lost, but your performance will be optimized because hard data is still in RAM, and you will gain in memory speed for your hottest data. That's fine. Let's move to using durability and achieving faster start and cheaper storing. All pages are present on disk in persistent mode, and when your in-memory region gets overflown, cold pages are now don't get removed. They are just removed only from memory. They are actually replaced to disk. That means your pages won't be lost. They will just be cleared from memory and still reside on your disk storage. It's easy to configure persistent mode in Ignite. You just take your configuration and set persistence enabled flag as true. And what will happen in result? When you fill your region with data, data will be present in two places, both in memory and on disk. And then when you continue loading, at some point your in-memory limit will be exceeded, and at that point your oldest and coldest pages will be replaced to disk. So all of your data set will be present on disk, and only the hottest pages will be present in memory. And you still have the durability guarantees. If you reboot your cluster in such state, state of all pages, independently of whether they are not present on disk or in memory, will be recovered. And more understandable and specific pattern is hot and cold data separation. And in case you have historical data set, for example, for history of all of your transactions, and probably you don't access history very often, and operational data set which encloses current state of your accounts, you may want to divide your data into hot and cold, and pattern is to configure small persistent region for big and cold data set, and to configure large memory region for small but hot data set that still requires in-memory speed. Here is how to configure. So you just specify two regions and set different limits for each of them and different names, and you link your caches with regions by specifying data region name in cache configuration, and that is what will happen. You have, for example, two hot caches A and B, and they reside in your hot big region. And you have cache C with historical data set, for example, audit information and history of all of your transactions. And when your cache C gets in memory chunk of cache C gets overflown, your data is just transferred from memory to disk. And on the one hand, you gain in memory speed when you work with your caches A and B because they are present in memory. And on the other hand, you gain durability and availability of your data in persistent mode in cache C, perhaps with not such good speed, but your data is still present, persistent, and won't be lost. So your history of transactions is resting in cache C, and all your operational data is accessed with a low latency in a big region. That's fine. And there's another case when persistence works and it's data backups. And now I'll tell you how to use it in Apache Ignite or GridGain and how to use it in different scenarios. First of all, why you may want to use data snapshots. First of all, it's obvious it's disaster protection. If something bad happens, you just recover to the previous point of time. And another use case that you may want is optimization. If you perform data snapshots at regular basis, for example, every day at 6 o'clock, if you have a cold data set, it isn't really gets changed from day to day. And you may bump into a situation when you snapshot the same data again and again every day. And this is what can be optimized. And I'll tell you how to optimize snapshotting of cold data in GridGain. And sometimes local snapshots may be not enough because, for example, you may experience complete disaster when all your local disk folders will be wiped and snapshots as well. And there are some other cases when you may want to transfer your created snapshots to separate remote snapshot catalog, and I'll tell you how to achieve that. Okay, and in case you want just disaster protection, there's operation like snapshot create, and when you say snapshot create, background process is started, and it starts copying page by page all your state of pages from your disk storage to separate snapshot storage. And reverse operation for that activity is snapshot restore. You can just replace all your disk storage by previously saved state that is already present in snapshot directory, and you will copy it back, and for period of copying your cluster will be unavailable, but when the copying will be completed, you just start your Ignite or GridGain cluster, and you experience that state of all of your pages is equal to state that was saved earlier, and you will just continue working like nothing happened. Let's proceed to optimization and to case where you have big amount of non-volatile data. We have an incremental snapshot option for that, and when you execute incremental snapshot, only pages that were changed since last regular snapshot will be written. It's achieved by special tracking pages. So there is a kind of memory overhead. We allocate tracking page for a range of nearly 16,000 regular pages. And on that tracking page, we pre-calculate the information of whether or not a page had been changed since the last snapshot. So it's obviously 0 for non-changed page and 1 for changed page. And when you say execute incremental snapshot, we don't scan and we don't analyze where the page were changed. We just look into tracking page. Information is already up to date. And according to these bit masks, we copy or we don't copy the page to the snapshot storage. And in practice, incremental snapshots are profitable, so they take less space, and they are created faster because you don't need to move all of your data. And sometimes local snapshot can be not enough. It's a complete disaster case, and it's also a case when you want to create and save daily snapshot catalog for every day when you create snapshot. And in case you have, for example, 500 gigabytes of your data, if you create snapshot every day, sooner or later you will overflow your local storage, and obvious solution is to move your created snapshot to separate reliable network storage. And the other use case when local snapshots are not enough is restoring after topology change. Imagine a situation where you have created a snapshot, for example, and after that you have scaled up your cluster. You added more and more nodes. Some of old nodes were replaced because you want, for example, faster hardware. And after, for example, 4 months, most of the nodes that contained your old snapshot are actually removed from topology, and you can't restore that snapshot because you don't have the data. In case you have a remote snapshot storage where snapshot had been moved, you just access the moved snapshot and still restore independent of how your topology were changed. So what you have to do to perform a movable snapshots is move commands. First of all, you create a regular local snapshot, and then you say move, and that's the point when your data from the whole cluster is moved to separate reliable network storage. And that is what happens. There are, for example, cluster of 4 nodes. There are some partitions on each node. And when you create a local snapshot, its disk state is replicated and saved in the separate directory. And what happens next? When you say move, all your created snapshot data is moved to separate reliable network storage, and it's removed from your local cluster disk storage. So you don't occupy disk space in your cluster, and you have all your environment protected by keeping state of all of your data into separate storage. And even if topology was changed, all data partitions will be found. All nodes will just, every node knows that which data it needs to pull from the remote snapshot storage, and perhaps it will find it in subfolders of another nodes. But there is such abstraction as partition, and every node knows which partitions does it need, and all that data partitions will be found. Just a moment. Okay, with that durability mode, you can gain all aforementioned benefits, but you still may experience performance degradation, and now I'll explain why this may happen and how to handle it, and how to prevent surprise performance degradation in your production environment when you use durability mode. So let's start with performance tricks. And first of all, you should be aware that memory disk ratio affects performance directly. So some of your pages are present in RAM, and some pages are not present. And if you work with your data and you suddenly need a page that is not present, you will need to perform a synchronous read to pull it from disk. And every absent page will require such synchronous read, as it will, anyway, it will add latency. So here's an approximate graph. There are 2 lines. First line is it's blue, and it's operations per second value. And the red line is percentage of how much pages are present in your RAM. And you may see that performance is good when you have 100%, and when all pages are present, it's like a hot data case. But when your data moves from hot to cold, or perhaps when you just load more and more data, when it just don't fit in RAM, your performance degrades, and approximately with the percentage, approximately with linear dependency from your ratio. So what you have to do, if you're planning to go to production, you have to estimate this memory disk ratio, and perhaps you want to do preliminary load testing, which will show which throughput can be achieved when you have the corresponding memory disk ratio. Next point, it's also related with the disk. That's if you apply peak load throughput to a system, it may be higher than overall of your disk throughput. And what will happen in such case? Here's a typical pattern of operations per second amount, dependent of load time, in case your disks are not fast enough and they are slower, they can't handle all of your system throughput. At the beginning, your operations per second ratio is fine, but at some point it suddenly drops to 0 for some time, and then it recovers, and it still continues to drop to 0 from time to time. Why such a thing is happening? The answer is that we have a checkpointing process, and we have to trigger checkpoint when amount of dirty pages is high enough. And when you have triggered checkpoint, you continue to accumulate dirty pages, but you may bump into the situation where checkpoint is not finished yet, and you have already used and made all of your pages dirty. And in such case, you can't continue working, you can't update all of any more pages because threshold is already reached, and checkpoint is not finished yet. So your disk throughput became a bottleneck. What we can suggest you to do is to switch write throttling mode to true. What is write throttling? Write throttling is a feature that Apache Ignite has, and when this mode is enabled, we estimate how fast we write to disk, and if the load is generated faster than that, we apply throttling to our threads that modify and make pages dirty. Basically, we slow the load a bit and what we want to achieve is to nearly equalize your load and your disk throughput. So when this mode is switched on, your peak throughput will be high at the beginning, and then when the disk load will start and throttling will be enabled, your overall throughput won't be such high, but you certainly won't see any zero drop downs. And this is beneficial because if you want latency, if you want system with latency requirements, for example, you want something some number of millisecond limit for each transaction, you just enable throttling, and overall throughput will be less, but latency will fit your requirements because there won't be situations when all your updates will be blocked by the fact that you have expired your RAM and filled it with the dirty pages. And another surprise that may strike you in production is specific behavior of SSD disks. SSD have the same low-level interface like HDD. They are designed to be easily adapted by operating systems. And they have an interface like write some bytes to that address, just like hard disk drives. But actually, solid-state disk drives are complex computers itself because they have a RAM buffer, they have a processor, they have a flash controller, and only on lowest level of abstraction, they have actual flash memory where your data is stored. And now I'll tell you some details about SSD implementation, which will explain why bad things may happen. SSD disks has pages and blocks, and page is something like 4 kilobytes, and pages are united and conjoined into larger blocks, for example, 64 pages. And the point is that on SSD data is written in page granularity, but it's erased in block granularity. You can't write already written page. First of all, you write only blank page, and to make pages blank, you have to erase data from it, and data can be erased only on block level. The physical reason for that is you have to apply higher voltage to your page in order to make it clean, and if you apply a high voltage to small page, it just interferes with neighboring pages, and your data may be corrupted. So they have grouped pages into blocks, and blocks are isolated from each other. So you apply high voltage to the old block. And imagine that you want to free some of your pages and you want to erase the block, but most likely that block that you want to erase contains some useful data. And what SSD controller have to do is to shift that useful data to another block. And when you, it's counterintuitive, but when you apply high load on your disk, it actually moves your data from one flash package to another flash package because it needs to erase outdated data, and the only way to erase is to apply high voltage to the whole block. And there's a fact that shifting is easier when more free blocks are available. And here's the graph. There are several lines. It shows the dependency of speed. It shows how speed is dependent from percentage of free space on your SSD drive. And different colored lines are different load patterns. There's a green line when load pattern is absolutely predictable. It's when you just write data in append-only manner. And the red line is the most unpredictable pattern with higher entropy. It's when all your updates are random. And the graph shows that in case your pattern can be easily predicted, throughput is really different. Yeah, when you have 80% of free space, your throughput is three times faster than when you have nearly zero free space. And what you need to know is when you want to boost your production throughput, you may want to keep some space free in order to increase the throughput. And the next surprise is that SSD performance issues do not appear immediately. So here's the results of experiment when high load has been applied to different models of SSD drives, and its dependency of time of the experiment to IOPS, how fast the throughput was. And what you may see is that at the beginning throughput is good, but then after 20 or 30 minutes, suddenly throughput degrades to lower level, and then it slowly goes to the saturation level, which is even lower. That is explained by the SSD architecture that it actually shifts data from blocks to blocks, and we can call such activity as garbage collection. And at some point, first of all, you just run out of your free space on your drive, and at this moment, garbage collection activity is no longer able to keep up in background. You have to slow down your activity in order to continue shifting blocks. And so to sum it up, if you want to measure how your system will behave, you have to try long load benchmark, which should be longer than tens of minutes, in order to estimate how really your system will behave for periodic, in case of long load. And another helpful feature that may will be handy to you is, first of all, every data update is written twice in persistent mode. First of all, it's written to write-ahead log, and it's written in synchronous manner. And also, in asynchronous manner, it will be written as part of checkpoint process. And in case you don't want durability guarantees right now, but you want to load big amount of data into a cluster, you can disable write-ahead log on purpose. In such case, you will disable the first part of activity and you will save only the second part. And in such case, you will not rewrite your data twice, you will do it only once, and crash recovery will be not guaranteed for such period, but on the other hand, you will gain at least 2 times throughput boost. So keep it in mind. It will accelerate your preparation of your production environment. And how to do this is just to call method disable wall on Ignite cluster interface. You can specify cache where you want to disable load. And after that, durability guarantees will be lost, but on the other hand, you will gain better throughput. And the last point is that Ignite node has 4 disk write activities. It's aforementioned checkpointing, writing write-ahead log. It's also transferring all the write-ahead log segments to write-ahead log archive directory. And it's data snapshotting. And in practice, all these 4 activities will compete on your single hard drive device. And how can you optimize it is just to specify different paths in configuration for each of these activities. And in case the paths that you have specified are mapped to separate physical devices, there will be no competition anymore. Every activity will write with its own hard disk drive, and overall throughput of your system will be better. So to sum it up, let's pass through performance tips again. You have to plan your memory disk ratio before going to production. You may consider using throttling if you want to achieve limited latency. You have to overprovision your solid-state disk drives in case, in such case, your throughput will be better. If you want to perform initial data load, you may just disable write-ahead log. And at last, you may want to split disk activities if you have an option to build separate disk storage devices. And in such case, all your throughput will be divided into these hard drives. So, to sum it up, personally, I will be happy if you'll consider using our persistent mode, especially if you're already using Ignite in memory deployment. First of all, you will gain all of those benefits. You will probably make your deployment cheaper, and you will gain durability and ability to hot restart and so on. And us, as Ignite developers, we will be highly motivated that our durability more than useful, and we will continue building it more and more flexible and easy to use. And working together, we can perfect it and probably adding some new features and fine-tuning the performance. So, thank you for your attention. I'm now ready to answer your questions. Yes, please.
Can you control the throughput, the number of threads for the throttling of the writes? Can you set the parameters yourself, or is it whatever you decide?
Basically, you don't. So in practice, when you use throttling, you don't. Well, first of all, there's an option such as concurrency level, and it's allows you to create more abstractions for handling persistence mode. So when you anticipate that you will have a bigger amount of threads, you may adjust your concurrency level. But when you use throttling, you perhaps don't want to limit the number of threads. You just want to limit overall amount of activity that they produce. So just even in case you have a really big number of threads, you just enable throttling and you don't have to worry about anything more. So all of your hundreds of threads will be limited and throttled in the same and equal manner. And the overall load won't exceed the disk throughput.
We have a scenario like applications RAM itself is 2 GB is enough, but when we have a cache layer, assuming that 80 GB, but when we are accessing the data through my application, it's getting out of memory sometimes. Further, just we have to increase our RAM for that application. Why it's like that?
I'm sorry. Can you repeat the question?
So we have application layer, then cache layer.
Cache layer, okay.
Yeah, cache layer 80 GB.
Okay.
So set max size is just we mentioned that 80 GB, but application layer just 2 GB is enough to run this application. But when we are accessing throughput frequently, our application is getting
Okay.
out of memory.
Okay. Let's talk about it probably after the talk. Okay.
For the snapshotting feature you talked about, is that available in all editions of Big Game, or is that only in the Ultimate Edition? Snapshotting?
Yeah, the truth is that snapshot feature is in Ultimate Edition of Grid Gain.
Once data is classified as code, as in it gets kicked out of memory into the disk, does it always stay as code data, or does it get brought back into memory if you access that?
Of course, if you access your memory again, it will be just uploaded from disk to RAM.
So you can't classify, for example, if you want to classify that as historical data, and you're happy with slow performance with respect to the data, can you not pin that data to disk?
No, so the point of transparent page memory architecture is when you need to work with page, it must be in memory because you execute some code and it assumes that page is loaded. So you can't work with page in right on disk. You have to load it to RAM anyway. But what you can do is to specify a very, very small region for the memory that is present that is called, and for example 1 GB. And in this way, only pages that you are working with right now will be present in RAM.
So the dirty page, the checkpoint, right? So the dirty page should be large enough to go to checkpoint, right? What is the maximum limit, or how do you calculate the checkpoint frequency?
Yeah, exactly. We have an option to configure the checkpoint frequency, and you may say that you want checkpoint to happen every minute, and in such case, it will be triggered by schedule. But it may be triggered anyway if your dirty page threshold is already reached. So checkpoint may happen faster if your load is high. Yes, but anyway, they will happen on time if you have specified frequency.
We have tried that option, but the performance rate is degraded after frequently set the threshold setting that. Why people may know the reason why it is happening?
Well, you have decreased the frequency, yeah?
Yeah.
That is understandable. So when you increase frequency, you mean that you made frequency lower, yeah, from 3 minutes to 1, for example, or you made it bigger. So what I want to say, if your checkpoint frequency is low, if checkpoints happen really often, every time when you update your page, it will be checkpointed to disk. And if your checkpoint frequency is bigger, like 5 minutes, some of your different updates that work with the same page will batch up. Yeah, the only one time page will be written to disk during checkpoints, and many operations can work with this page without writing to disk. So lower checkpoint frequency is. So you may want to specify bigger checkpoint frequency, but it will strike you because you can reach the limit. So there's a balance. So if you want to maximize your throughput, you can increase the checkpoint frequency, but in such case, you should have enough of RAM. Okay, one last question, please, and then it's time. Please.
Can you pause updates? Can you switch the cache from Tephra into read-only mode in order to guarantee checkpoints?
No. Checkpoints are performed under load. So what is happened inside is for the one moment set of dirty pages is fixed and its checkpoint is start working, but checkpoints are actually performed under load. So you will not even see the drop down on your operations per second graph. So they are performed on the fly. So checkpointing is background process. So I guess that's it. Thank you again.